Hello and hi everybody. Today we want to present to you about redox titration. Our group members, first we have one Emily Jasmine, Nur Aisyah SAFFIYA, Nur SYAMIMI NAJWA, FARAH ASMAH and ALYA MAISARAH.
Before we start, let us know what is redox titration. In separate words, redox means chemical reaction that involves the transfer of electrons between two substances. One substance loses electron, we call it oxidation, and the other gains electron, we call it reduction. The letter R in redox means reduction and OX means oxidation. Titration means a technique that used to find the concentration of a solution, we call it analyte. By slowly adding a solution with a known concentration, we call it titrant. This process continues until the reaction is complete, which is usually shown by a color change. Combining these two words, we got the meaning of redox titration, which means a method based on oxidation reduction reactions used to determine the concentration of an unknown solution through electron transfer. For the next slide, we need to know why redox titration matters. The first purpose why it matters is to measure concentration. This means that it could determine the amount of oxidizing or reducing agents in a sample. The second purpose is to understand redox reaction. This means that it could show how substance gain or lose electrons during a reaction. The third purpose is to detect reaction completion. It could identify the exact point a reaction finishes using color change or voltage measurement. And the fourth purpose is because redox titration could be used in wide application, such as pollution testing, food quality like vitamin C, and drug manufacturing. So, what is the objective of redox titration? The first one is to find the exact concentration of oxidizing or reducing agents by reaching the correct endpoint in a redox reaction. The second objective is to learn how electrons are transferred and how oxidization states change during the titration. And the last one is to support quality control in industry like food, medicine, and environmental monitoring.
So, for the theory and principle, redox titration is a technique that uses a chemical reaction in which one substance loses electrons, oxidizes, and another substance acquires electron to reduce to determine the amount of a substance. Until the reaction is finished, a titrant, a solution with a known concentration, is introduced to the unknown solution. So, for the first one, which is oxidation. Oxidation is a process where a substance loses electrons, which can occur by addition of oxygen, removal of hydrogen, loss of electrons, and an increase in the state of oxidation. Next, reduction is a process where a substance gains electrons, which can occur by addition of hydrogen, removal of oxygen, acceptance of electrons, and decreasing in oxidation state. Next is detection of endpoint of the titration. So, the endpoint of a redox titration is detected by three indicators. For the first indicators is redox indicators, which is a special chemicals used in redox titrations to show the endpoint of the reaction. They change color when they are oxidized or reduced, helping us see when the reaction is complete. Thus, these indicators react quickly and the color change is easy to notice. So, for the second indicators is self-indicators, which is also known as chemicals that change color on their own to indicate the endpoint. No further signal is required because they react by changing or losing their vivid color. The last indicators is potentiometry, which is the endpoint is determined by measuring the voltage between two electrodes rather than by looking for a color shift. Redox exhibits complexometry and precipitation titration can also benefit from this. Next is titration curve. So, what is a titration curve? A titration curve is a graphical representation that shows how the pH of a solution changes as the volume of a titrant is gradually added during an acid-base titration. These curves can vary widely depending on the specific acid and base involved, and they are important for understanding the behavior and strength of acids and bases throughout the titration process. So, typically, the curves start with a slow, gradual change in pH, followed by a sharp and steep rise or drop at the equivalence point, then finally levels off as the titration reaches completion.
Next, for methodology, we have apparatus and chemical reagent. For apparatus, we use 25 ml volumetric flask, 50 ml puree, conical flask, magnetic stirrer, safety goggles, gloves, lab coat and waste container. For chemical reagent, we use iron supplement tablet, distilled water, 0.02 mol dm potassium permanganate solution, 1 mol dm sulfuric acid and phenolphthalein indicator. Next, preparation of iron solution. First, crush the iron supplement tablet into a fine powder using a mortar and pestle. Secondly, weigh out a sample of the iron tablet powder that is approximately 0.1 or 0.2 gram and transfer it to a 25 ml volumetric flask. Next, add 10 ml of 1 mol dm sulfuric acid to the flask and swirl to dissolve the tablet powder. Next, dilute the solution with distilled water to the 25 ml mark on the volumetric flask. Lastly, transfer 25 ml of the iron solution to a conical flask. Last, standardize of iron solution. First, we need to add a few drops of phenolphthalein indicator to the iron solution. Next, fill the burette with potassium permanganate solution. And then slowly add the potassium permanganate solution to the iron solution while stirring with a magnetic stirrer. Next, the solution will turn purple as the potassium permanganate oxidizes the iron. Continue adding the potassium permanganate solution until the purple color disappears, indicating that all of the iron has reacted with the CHM256. Record the volume of potassium permanganate solution used to reach the endpoint. Repeat steps 5 until 10 2 more times to ensure reliability of the titration. Lastly, calculate the average volume of potassium permanganate solution used to reach the endpoint and use this value to calculate the concentration of iron in the tablet.
Next is results and calculation. Results, reaction mechanism. The reaction between iron in the tablet and potassium permanganate can be represented by the following equation. The reaction is 5Rm2 plus MnO4 minus plus 8H plus. The product will be 5Rm3 plus Mn2 plus 4H2O. In this reaction, the potassium permanganate is reduced to manganese ions, while the iron is oxidized from iron 2 plus to iron 3 plus. The phenolphthalein indicator is added to the solution to act as the visual signal for the endpoint of the titration. The solution will turn from colorless to pink when all the ferrum 2 plus has been oxidized to ferrum 3 plus. Results table. In this experiment, the following table shows the results obtained from the iron tablet titration. Average volume of CHM256 solution used in milliliter for trial 1, 14.7, for trial 2, 14.9 and for trial 3, 15. Next is the calculations. To calculate the concentration of iron in the tablet, we can use the following formula. Concentration of iron, volume of potassium permanganate times molarity of potassium permanganate times atomic mass of iron divided by volume of sample times 5. Assuming that the molarity of the potassium permanganate solution is 0.02 mol cubic decimeter and the atomic mass of iron is 55.845 g per mol, the calculation would be as follows. Concentration of iron, volume of potassium permanganate is 14.9 ml times molarity of potassium permanganate is 0.02 m times atomic mass of iron is 55.845 g per mol divided by volume of sample is 25 ml times 5. Therefore, the concentration of iron in the tablet is 11.274 milligram per ml. The above calculation assumes that the entire sample was dissolved in the 25 ml volumetric flask. If the entire tablet was not dissolved, the result may be inaccurate. It is important to ensure that the tablet is fully dissolved before conducting the titration.
In our conclusion and evaluation, we considered that have four key aspects. Firstly is accuracy. The amount of iron we found was very close to the value on the label. This means our titration gave a correct result. Secondly is environmental impact. We use chemicals like potassium permanganate and sulfuric acid, which can be harmful, so we made sure to throw them away safely to protect the environment. Thirdly is safety. We wore safety goggles, gloves, and lab coats. We were careful when handling the chemicals to avoid accident. Lastly is sources of error. Some things that could cause mistake are not fully dissolving the tablet or not handling the solution properly. So this could make our result less accurate.